All right, here we go again with Lesson 9, Solving Exponential and Logarithmic Equations, Part 2. So here we go with this first set of equations. We're going to be looking at logarithms, and we'll be using an exponential to solve them. Remember in the last lesson, we had equations that had exponentials, and when necessary, we had to use a logarithm to cancel out the exponential. So it shouldn't surprise you, since they're inverses, that we'll use an exponential to cancel out a log. So since this is log base 2 of x equals 3, I'll be taking the exponential with the base of 2. So 2 to the log base 2 of x must be equal to 2 to the third. So I'm kind of using that one-to-one property of exponentials we talked about in the last lesson. That if log base 2 of x is the same as 3, then using them as exponents to a base of 2 would get me the same value as well. Now, the 2 to the log base 2 of x cancels out and gives me just x. Why it does, you could take it on faith, but it's worthwhile considering why that's happening. So let's think about that for a second. 2 to the log base 2 of x. Well, let's pretend that we knew that answer was some answer, I'll call it p, okay, for power. So whatever that value is, well, oh, actually, you know what? I did that in the wrong way. I want to instead let's start by just looking at the log base 2 of x. Let's say that is equal to some power p. So that whatever that value is, we know that by properties of the definition of a logarithm that means 2 to the power p is equal to x. So what happens if I have 2 to the log base 2 of x? Well, we know that the log base 2 of x is some value p, and that p is defined to be the very number that when I raise 2 to that power will give me x back. So that's why 2 to the log base 2 of x gives me just x. All right, so now we got that settled. Let's go through what this would be. This cancels, and 2 to the third, be real careful how you do that. It's not 3 to the second, it's 2 to the third is 8. Now, when we're solving logarithms, they have a restricted domain. We really need to be checking for extraneous solutions. You don't really necessarily have to check that the answer is 100% correct as much as check that the answer is in the domain, that it does not cause you to get a 0 or a negative number in a logarithm. If I plug in 8 for x, I get the log base 2 of 8, which is indeed 3. Certainly in the domain, so we're good. So the answer is 8. Let's take a look at the next one. Earlier we saw that we used an exponential of 2. Here I'm going to use the exponential with base 3. So I call this 3 to the. I'm to-thing both sides. 3 to the log base 3 of x minus 1 equals 3 to the second. Those cancel out, giving me x minus 1 equals 9. So x equals 10. Plugging in 10 and checking is perfectly okay, so we are good to go. We call that the answer. All right, now in this next one, we can use the one-to-one property of logarithms. It says if one log equals another log, then their arguments must be equal. Or this is log base 10. We could think of it as exponentiating both sides with a base of 10. Either way, you get x squared minus x equals x plus 3. And since this has got an x squared in it, you should be thinking, okay, I have to set this equal to 0. And when you do so, you can factor it like so. And get x equals 3 and x equals negative 1 for your values. Neither one of those give me a negative in a logarithm, so we are good to go when calling both of them the right answer. So you look at the next one. Again, because they're both inside a logarithm, we can set them equal to each other. Or if you prefer to think about it, we're raising each side to the power of e, which cancels the logarithm. So 2 to the x squared minus 3 must equal 5x plus 4. Again, I set this equal to 0, and I get 2x squared minus 5x minus 7 equals 0, which factors as 2x minus 7, x plus 1, giving me x equals 7 over 2 and x equals negative 1. Unfortunately, the negative 1 doesn't work, because if you plug it in to say 5x plus 4, you'll get that it is in fact a negative number, and that's not allowed. Even though it says natural log of negative 1 equals natural log of negative 1, any negatives in logarithms are outside our domain. We cannot accept them. So our only answer is 7 over 2, which does give us a positive, two positive numbers in the logarithms. So that is our only solution. All right, I've got 4 little practice problems for you to do right quick. Give them a try. Pause the video, please. Give it your best shot before moving forward. All right, let's try the next one. Now, don't think this is no solution, because it's all right for a logarithm to equal a negative number. We just can't have a negative number in it. I hope you remember that the base of this logarithm is 10. So I'm putting both sides as an exponent of 10. 10 to the log is just x, and 10 to the negative 2 is 1 over 100, 1 over 10 squared. On the next one, we should put each into a base of 4. So 4 to the log 4x minus 2 equals 4 to the second, giving me x minus 2 equals 16, or x equals 18. And that checks just fine. All right, over here, we need to raise both sides to the 10th, 10 to the, I should say. And I get 12 plus x squared equals 3 plus 2x squared. Setting this equal to, well, actually, I'm not going to set it equal to 0 because I don't have an x term. I'll just isolate the x squared. Subtracting x squared over gives me 9 equals x squared. Taking the square root gives me plus or minus 3. And in fact, both plus and minus 3 work just fine. Neither give me a negative in the logarithm, so we are good to go. Good to go with both of those answers. All right, let's try the next one. On this one, we need to isolate the log base 2. So I am going to subtract 2 from both sides. Then I'm going to divide both sides by a negative 3, giving me a positive 3. And then exponentiate both sides, giving me x minus 1 equals 8. So x equals 9, which checks just fine and dandy. All right, let's go on to some more problems. Let's use properties of logarithms to solve the following equations without a calculator. All right, so with these problems, we're going to have to remember that when you have logarithms with pluses in between them, it's times on the inside. So if I had the log of a plus the log of b, that we can condense that to the log of ab. Likewise, if I had the log of a minus the log of b, I can condense that to the log of a over b. We need to remember those properties. And that's important because I cannot exponentiate both sides like we've been doing if I have anything else but just a single log on one side of the equation. I can have log equals log or log equals number, but I can't have a log plus a log. So this is not okay to exponentiate yet. Does not work. But I can combine them and call this the log base 2 of, and I multiply the arguments, and I get x squared plus 3x. And that needs parentheses because of the plus. Then I just make each side the exponent to 2, cancels out that, giving me x squared plus 3x equals 4. Then setting this equal to 0 and solving. Factors is x plus 4, x minus 1. So x equals negative 4 and x equals positive 1. But unfortunately, the negative 4 gives me a negative in the original logarithm, so it's not okay. It actually gives me a positive number here, but it gives me a negative number in the original problems before we can then combine the logarithms, so it is not okay. So the only solution is 1. All right, let's try the next one. The log of 5x minus the log of 3x minus 1. Here, we need to divide because we have subtraction on the outside. Now that I've got it convinced, I can exponentiate both sides with the base, and the base of this log is 10. So I get 5x over 3x minus 1 is equal to 10. Now you can remember your cross product from middle school. This times this equals that times that. Or you can just realize we just need to multiply both sides by 3x minus 1. And I get 5x, because that cancels out, equals 30x minus 10. So x is equal to, I think, 2/5. And 2/5 does not give me a negative number in a logarithm. It gets kind of close, 6/5 minus 1, but it's okay. So that is the solution. All right, got a couple now for you to try. Please try those problems. All right, let's see how you did. All right, well, the logs are on two different sides, but because of this 2 here, I can't exponentiate right now. I need to move it over. So I'm going to move over this log and make it plus log base 3 of x plus 1 equals 2. Then since it's plus inside, I'm going to multiply, giving me 2x squared plus 2x minus 5x minus 5. When I FOIL these two together, exponentiating both sides, 3 to the, 3 to the, and I'm going to go ahead and combine these two here. 2x squared minus 3x minus 5 equals 3 to the second is 9. Setting this equal to 0. And I get 2x, I think it's minus 7 and x plus 2. Let's see, 2x squared plus 4x minus 7 is negative 3x minus 14. It's good. So x equals 7 over 2, and x equals negative 2. The negative 2 is definitely not allowed. I think the other one is fine. Yeah, it is. So 7 over 2 is our answer. All right, let's take a look at the next one. You should have combined them with division. So it becomes 12x plus 3 over 2x plus 1 is equal to 1. Exponentiate both sides with a base of 5, and you get 12x plus 3 over 2x plus 1 is equal to 5. Then multiply both sides by 2x plus 1 to cancel it from the denominator. Don't forget to distribute the 5, and you get 12x plus 3 equals 10x plus 5. And solving that, I think you get just x equals 1. Yeah. And that 2 plus times 1 plus 1 is 3. 12 plus 3 is 15. So that's fine. So it doesn't give us a negative in the logarithm. That's our answer. All right, let's take a look at some more questions here. These are going to require a calculator to get an exact, an approximate answer because of the base e and things like that. So look to see how we handle that. 3 times the natural log of x minus 2 equals 7. I'm going to divide both sides by 3, and I get the natural log of x minus 2 equals 7 over 3. Then I need to put each side as an exponent, the exponent of the base natural log, which is e. That cancels out, giving me just x minus 2 equals whatever e to the 7/3 is, and I would need a calculator to get that. The exact answer then, we could say, is e to the 7/3 plus 2. But let's go ahead and get a decimal on that. So e to the 7/3 plus 2. Having trouble clicking. 12.312. All right, let's try the next one. All right, we need to combine these logarithms. So we get 2x minus 3 over x is equal to 3. And then exponentiate both sides, and you get 2x minus 3 over x equals e to the 3rd. Multiplying both sides gives me 2x minus 3 equals e to the 3rd times x. Now this is a little bit challenging because we have to add e to the 3rd x and 2x. You might find it easier to go ahead and get a decimal right now, but let me show you how you would handle this. Subtracting the 2x to the other side. What I'm going to do is factor out an x, and when I do that, I get e to the 3rd minus 2. So that's the trick on how to do that. Then we can give the exact answer as negative 3 over e to the 3rd minus 2 equals x. So let me figure out what that is. Negative 3 divided by e to the 3rd minus 2. Negative 0.166. Ooh, but that gives me a negative number inside the this logarithm. Let me make sure I typed that incorrectly, but I think that's right. When I multiply that over, I get e to the third. E to the third times x equals 2x minus 3. We subtracted the 2x over. Yeah, I don't think this has a solution. I'll tell you what, let's confirm. Okay, so I graphed the left-hand side of the equation in Desmos and the right-hand side y equals 3. I can say y equals as well here. But I think what we're going to see is that while this is rising always, it's never going to actually reach the 3. It never actually reaches a height of 3. So this is not going to ever equal each other. It's very interesting that it would have a horizontal asymptote like that, but it just does. Because I think it doesn't go any higher than the natural log of 2. So I think it kind of taps out at 0.693. Yeah, that's exactly what happens. So there we go. No solution on that one. We only got one answer, and it made a negative in the radical, so no solution. All right, let's try the other ones. 4e to the 2x minus 1 equals 7. So I will add 1 to both sides and divide by 4. Then I'll take the natural log of both sides, and I get 2x equals the natural log of 2. So x is the natural log of 2 over 2. And the natural log of 2 divided by 2 is 0.347. And that is perfectly fine. There's no logarithms there, so I don't have to worry about extraneous solutions. Now let's try this one. I'll divide both sides by 3. And I'll use the natural log. X times the natural log then of 1.09. Remember, I'm bringing the x down in front. Equals the natural log of 8/3. So I have the natural log 8 over 3 divided by the natural log of 1.09. And I get 11.381. You know, I don't know if we've seen this or reviewed this yet since the last lesson, so let's just go ahead and remember. So recall what's happening here. I'm taking the log, or natural log actually is what I chose. Remember, you might remember we said it doesn't matter as long as we do the same logarithm on each side. And we're using the property that if you have an exponent in a logarithm, it can come down in front of it. And so that's how we get to that step there. Okay, I just oftentimes skip that step since it's so immediate. All right, I've got a few problems for you to practice doing, so please give it your best shot. All right, let's see how you did. We would divide both sides by 4 and get the natural log of 5x is equal to a half. Let's say 0.5. And then I will exponentiate each side with the base of e, so I get 5x equals e to the 0.5 and divide by 5. So e to the 0.5 divided by 5. We can get a decimal approximation there. Is 0.330. There we go. I think that was right, wasn't it? 3 point, yeah. Let's try the next one. We've got the natural log isolated, so we'll just exponentiate both sides, giving me x plus 2 is equal to e to the 4th. So my x is e to the 4th minus 2, which is a perfectly good answer. It's an exact answer, actually. But let's get an approximation. E to the 4th minus 2 is 52.598. All right, let's try another one. I'm going to add 2 to both sides, so I get 4e to the negative 2x is equal to 1. So e to the negative 2x equals 1/4, and we'll take the natural log of both sides. Give me 2x equals the natural log of 1/4. And divide by a negative 2. And I don't need to worry about extraneous solutions because this is an exponential, so it should work just fine. The natural log of 1 over 4 divided by the negative 2. .693. All right, let's try the next one. Isolate the r, and we get 1 plus r to the fifth equals 4. This is not a logarithm problem. This is one where we're going to use roots. So we're going to raise each side to the 1/5 root. So r is 4 to the 1/5 minus 1. And we can get a calculator approximation again. So 4 to the parentheses 1/5 minus 1. And that value is 0.3195 or 0.320. All right, there we have it. All right, got just a little bit more banking review. Let's find the missing information about a savings account with an original investment P, rate of interest for the year of R, compounds for year N, years T, and an in balance A. Show and label your work below. All right, so I want you to give it your best shot to fill in this table of values. It gives you 4 different problems to do. All right, well, this is how you should have done that. You should have said that my account balance A is equal to principal times 1 plus the interest rate divided by the number of compounding periods to the power of the compounding periods times years. So my first problem is 1,000, then 1 plus an interest rate of 0.05, done 12 times a year, to the 12 times t. And that is supposed to equal an ending balance of 3,000. And I need to find the missing t value. So this is 1 plus 0.05 over 12 to the 12t equals 3. Taking a natural log of each side, let me go ahead and get a decimal on that middle value there. 1 plus 0.05 over 12 is 1.00417. So 1.00417 to the 12t equals 3. Now, if I take the natural log of this, I can bring the 12t down, and I have the natural log of 1.00417 equals the natural log of 3. So I can say the natural log of 3 divided by the natural log of 1.00417. Which gives me 264.005. Which we get to, fortunately, divide by 12. Giving me, forgot to divide. 264.005 divided by 12 is 22.000, so about 22 years. All right, let's try the next one. We're going to look for the number of years to get 4,000, given that I'm just going to go ahead and erase this work. If you need it, pause the video, but I'm going to erase it so I have some room here. All right, so I've got 25,000 to start with a 4% interest rate that's compounded just twice a year to the 2 times the number of years. When does that equal 4,000? Dividing both sides by 2,500, and I'll go ahead and simplify that decimal. That's going to be a 1.02. And what is 4,000 divided by... I can set this where it leaves it up. All right, let's see here. We need 4,000 divided by 2,500. Four 25ths or 0.16. taking the natural log of both sides, bringing down the 2t. So the natural log of 0.16 is going to be divided by the natural log of 1.02. Oh, you know what? I put too many zeros earlier. Okay, so I need to go back and change that. Hold on. I got the wrong number here. This should be a 1.6, shouldn't it? Yeah. So this value is wrong as well. I'd say pretty unreasonable answer we were getting there. All right. So the natural of 1.6 divided by 1.02. Let me just change this, move this decimal place right quick. Gives me 23.734, which we can then divide by 2 to get 11.867 years. All right, it's time to do another one. Okay, this time we don't know the necessary starting principal in order to get 2,300 in 12 years. So we don't know the principal. 1 plus 0.045 over 12 to the 12 times 5 years needs to equal 2,300. Well, believe it or not, all this gunk here is really just some number. We can just evaluate that. That's 1 plus 0.045 over 12 raised to the power of 12 times 5. So that value is 1.2518. So then I'll divide 2,300 by that value. Giving me a principal of 1837.35. That's what needs to be my initial deposit if I'm going to make that much money in those 5 years. All right, one more. What kind of interest rate do I need to get $1,000 to become $1,500 in 6 years? And this is compounded only once a year. So 1,000 times 1 plus what interest rate to the power of 6 does that equal 1,500? All right, divide both sides by 1,000 and you'll get 1 plus r to the 6th is equal to 1.5. And then technically I need to take the 6th root of both sides, which means I need plus or minus. But we're going to ignore the plus or minus in this situation because it just doesn't make sense in the domain of the problem situation to have a negative interest rate. So notice how I put the 1/6 in parentheses when I raise it to that power. There is an x root function if you want to put 6 and then find the x root function, but I'll just put 1/6 power. It makes more sense to me. Well, I get 1.06991. Then I can subtract 1 from that to get just 0.06991, or 6.991%, which is a really big interest rate. Okay, let's take a look at the x's again. I kind of like this one for today. The graph of y equals e to the 3x minus 5 is shown below. Can you estimate the 0 from the graph and then find the 0 using algebraic techniques? Well, it looks like the 0 is just like maybe 0.6. Does that look like a reasonable answer? So let's find what the true 0 is. Recall that a 0 is when you set the equation equal to 0. So the equation for y equal to 0. Giving me e to the 3x equals 5. So 3x equals the natural log of 5. So x is equal to the natural log of 5 over 3. Notice we took the natural log of both sides to cancel out that e. Okay? And the natural log of 5, I'm not sure what that is, divided by 3 is about 0.536. So we had a pretty good guess for ourselves. So the 0 is 0.536. All right, that's it for this lesson, and I'll see you in the next one.